On October 28th, 2025, Jensen Huang stood on a stage in Washington, D.C. and called something a Rosetta Stone, not a chip, not a product, a translation device between two entirely different languages of computing, quantum and classical, that had never truly been able to talk to each other at the speed either one actually needed. He promised it would mark the beginning of an entirely new era. 17 quantum hardware companies signed on that same day. 9 of America's most prestigious national laboratories backed it before it even shipped. Read that again. 9 months later, the champagne has gone flat, the keynote lights are off, and the only question that actually matters is the one nobody asks at a launch event. Did it work? To answer that question honestly, you first have to understand exactly what problem NVQLink was actually built to solve, because the hype around its launch often obscured just how narrow and just how genuinely difficult that original problem really was. Quantum computers have always faced a brutal, unglamorous engineering challenge that has nothing to do with how many qubits a company can cram onto a chip. Qubits are delicate, painfully delicate. A stray vibration, a whisper of ambient heat, and the fragile quantum state a calculation depends on simply collapses, taking the entire computation down with it. The fix has always required continuous, real-time error correction, a process that demands classical computing power sitting right next to the quantum processor, reacting to problems faster than the human eye could ever perceive, catching and fixing mistakes before they spread and ruin everything. For years, every quantum hardware company solved this problem their own way, building custom, incompatible connections between their specific quantum chips and whatever classical computing power they happened to have access to. There was no shared standard, no common language. This is not chaos. This is simply what happens in the earliest years of any genuinely new technology, dozens of brilliant engineers solving the same fundamental problem in dozens of mutually incompatible ways, each one convinced their particular solution was the right one. NVQLink was Nvidia's attempt to end that fragmentation entirely, and the technical claim underlying it was genuinely audacious. According to Nvidia's own launch materials, the interconnect promised to exchange data between quantum controllers and classical GPUs at a latency of under 4 microseconds, a speed roughly equivalent to completing 100,000 round trips in the time it takes you to blink once. 9 of America's most respected national laboratories, Brookhaven, Fermilab, Lawrence Berkeley, Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest, and Sandia, all contributed to guiding the interconnect's actual technical design before it ever launched publicly, a level of institutional scientific involvement that separates a serious infrastructure project from a flashy corporate demo built purely for a keynote presentation. And the breadth of hardware companies willing to sign on that same day was, frankly, remarkable. 17 separate quantum processor builders, spanning superconducting circuits, trapped ions, neutral atoms, and photonic systems. Essentially, every major hardware approach currently being pursued anywhere in the field, all agreeing, on day one, to plug into the exact same interconnect, rather than continuing to build their own separate, incompatible solutions. Alongside them stood 5 companies specializing in the delicate control systems that actually operate quantum hardware in real time. This is where the story could have simply ended: another ambitious tech launch, another round of enthusiastic press coverage, another wave of skepticism, and then, eventually, quiet abandonment once the initial excitement faded and reality set in. That's the fate that eventually claims most ambitious infrastructure announcements in this industry. NVQLink's actual first year tells a genuinely different story, and the evidence for that difference arrived in stages, each one more concrete than the last. The first real test of whether NVQLink would become genuine, usable infrastructure rather than a permanent slide in future keynote presentations came in March of 2026 at Nvidia's GTC conference, roughly 5 months after the original announcement. This is the moment the promise actually had to become software developers could touch, and Nvidia delivered exactly that, releasing something called the CUDA-Q real-time API as part of its broader CUDA-Q platform. Think about the significance of that specific transition. An announcement is easy. Building the actual application programming interface that lets developers write real code, sending real data back and forth between a quantum controller and a bank of GPUs at genuinely microsecond level speed, that's considerably harder, and it's exactly the kind of unglamorous, deeply technical work that separates a company genuinely committed to shipping working infrastructure from a company simply chasing headlines. Alongside this software release, Dell independently validated 4 of its own server models: the XE45, the XE9680, the R77 and the R770 as certified real-time host platforms, successfully reproducing those same sub-4 microsecond latencies on commercially available, off-the-shelf hardware that any well-funded research lab could actually purchase. Read that again. because it matters enormously for answering this video's central question. This isn't Nvidia simply claiming its own technology works in its own internal testing. This is an entirely separate, independently respected hardware company running its own tests, on its own equipment, and confirming the same core performance numbers Nvidia originally promised. In science and engineering alike, independent replication is the single strongest form of evidence you can possibly ask for, and NVQLink cleared that bar just 5 months into its existence. But independent replication of a latency benchmark only tells you the plumbing works. It doesn't tell you whether anyone actually wanted to use that plumbing for something real, and this is exactly where the next several months of NVQLink's first year get genuinely interesting, because throughout the summer of 2026, a steady, verifiable stream of specific named companies began announcing that they had actually built real systems on top of this interconnect. Not just endorsed it in a press release, but genuinely integrated it into their own products and research programs. Atom Computing announced it had successfully integrated NVQLink directly into its own proprietary control system stack, the software layer responsible for actually operating its quantum hardware moment to moment. IQM, a Finnish quantum computing company, partnered with Zurich Instruments to build something called a real-time quantum error correction demonstrator, combining a 20-qubit IQM quantum processor, Zurich Instruments' own specialized quantum control system, and NVQLink itself, all working together as a single, integrated proof of concept. Think about what it means that two entirely separate companies, based on different continents, building different pieces of quantum hardware, chose to converge specifically on NVQLink as the connective tissue linking their systems together, rather than building their own custom, incompatible solution the way quantum hardware companies had always done before. The pattern continued to build throughout the following months, and each new example added genuine weight to the case that NVQLink had crossed from ambitious promise into working, adopted infrastructure. A company called Elevate Quantum launched something called QPAC, a commercially deployable open architecture quantum system built by combining components from 4 separate specialized companies: Quantware, QBlocks, QCTRL, and Maybell, with NVQLink-based GPU cluster integration explicitly written into its stated roadmap for later in 2026. Dirac, a company building quantum processors using silicon-based qubits, a fundamentally different physical approach from IQM's superconducting circuits or Atom Computing's neutral atoms, began using NVQLink specifically to connect its hardware to accelerated computing for calibration, auto-tuning, and benchmarking studies. The unglamorous but absolutely essential daily work of actually keeping a quantum computer running reliably. And in June of 2026, Quandela, a French company specializing in photonic quantum computing, technology that uses individual particles of light rather than superconducting circuits or trapped atoms, published a genuinely detailed technical case study explaining precisely why NVQLink mattered for their own specific corner of the industry. Their analysis identified a structural problem with how quantum cloud computing had traditionally worked, treating quantum processors as distant, remote resources accessed over a slow, high-latency internet connection, the way you might access a cloud storage server. NVQLink, according to Quandela's own engineers, solved this by creating a direct, dedicated path straight from a GPU's processing core to the actual quantum system controller during an active computing session, eliminating exactly the kind of latency bottleneck that had made photonic quantum machine learning genuinely impractical under the old architecture. Here's why this specific list of partners matters so much more than the original 17-company launch announcement, and it's worth pausing on this distinction carefully because it's the actual answer to whether NVQLink worked. A launch day partnership list costs almost nothing. Companies sign onto exciting new industry standards constantly, hedging their bets, wanting to be associated with whatever momentum happens to be building at the moment, often without any genuine intention of building real, load-bearing infrastructure on top of that standard. What happened over NVQLink's first 9 months was something categorically different. These weren't companies simply repeating Nvidia's name in their own press releases. These were companies publishing detailed technical case studies, integrating the interconnect directly into their own proprietary control software, and building entire commercial product roadmaps explicitly around NVQLink's continued existence and continued reliability. That's the difference between genuine adoption and empty corporate signaling, and by the middle of 2026, the evidence pointed unmistakably toward the former. Understanding exactly why so many fundamentally different companies, building fundamentally different kinds of quantum hardware, all chose to converge on the same specific piece of infrastructure requires understanding the precise technical problem sitting underneath all of it, the one NVQLink was engineered from the ground up to solve. According to Nvidia's own technical documentation, quantum error correction decoding represents what the company describes as a massive single-user inference task that has to run continuously alongside quantum processing itself with absolutely zero tolerance for delay. A quantum processor needs access to high-performance co-processing, capable of responding to function calls in real time, faster than its qubits naturally decohere and fast enough to track subtle system drift. The gradual, almost imperceptible wandering of gate fidelities that happens as quantum hardware operates over time. This is a genuinely narrow, genuinely technical bottleneck, but it's also one that every single quantum hardware company, regardless of whether they're building superconducting circuits, trapped ions, neutral atoms, or photonic systems, ultimately runs into in exactly the same form. Think about why that specific universality mattered so much for NVQ-Link's adoption. This wasn't a solution tailored narrowly to one particular kind of quantum hardware, the way so many previous proprietary control systems had been. It was a solution to a problem every quantum company faced identically, which is precisely why companies as different from each other as Dirac's silicon-based processors and Quandela's photonic systems both found genuine, independent reasons to build on top of it. Now, here's where this story needs the same honest, careful scrutiny we've applied throughout every video on this channel, because celebrating NVQ-Link's adoption without confronting its genuine limitations would be doing you a real disservice. The evidence gathered across NVQ-Link's first 9 months overwhelmingly supports one specific, narrower claim, that the interconnect works as advertised for calibration, control, real-time error correction, decoding, and hardware benchmarking. That is a genuine, verified, independently replicated technical achievement, and it should not be understated. But it's worth being precise about what that evidence does not yet show. None of the partner integrations documented throughout this first year represent an independently verified instance of NVQ-Link, specifically enabling some entirely new scientific discovery that would have been impossible without it, some breakthrough calculation or novel result that couldn't have happened through any other connective architecture. Claims genuinely proven are claims about infrastructure performing its intended plumbing function reliably. The claims not yet proven are claims about that infrastructure directly producing groundbreaking new science, and conflating those two categories would be exactly the kind of overreach this channel has tried to avoid throughout its entire coverage of the quantum computing industry. There's a second honest limitation worth confronting directly, because it cuts against the more triumphant, dominance-focused framing that surrounded NVQ-Link's original launch. Back in October of 2025, when the interconnect first debuted, several industry commentators predicted it would position Nvidia to dominate the entire emerging quantum classical hybrid computing market, essentially becoming the single, unavoidable standard every quantum company would eventually be forced to adopt. 9 months later, that specific prediction of outright dominance simply hasn't played out the way it was originally framed. IBM, one of the most credible and technically respected names in the entire quantum computing industry, remains conspicuously absent from NVQ-Link's list of adopting partners, continuing to pursue its own independent FPGA-based approach to real-time error correction instead. And in June of 2026, at the Quantum.Tech World Conference, Hewlett-Packard Enterprise announced its own parallel integration effort, working with an unusually broad coalition spanning Intel, IQM, Q-Blocks, Quantinuum, Quera Computing, Quantum Machines, Rigetti, and Riverlane, all collaborating to connect different styles of quantum hardware directly to HPE's existing Cray supercomputing platform. Think about what it means that this rival coalition emerged just months after NVQ-Link's own public API launch, built by a genuinely credible competitor, drawing on many of the same underlying quantum hardware companies that had also signed onto NVQ-Link's original launch. Some quantum hardware builders, it turns out, aren't betting exclusively on a single interconnect standard. They're hedging, building compatibility with multiple competing architectures simultaneously, exactly the kind of pragmatic, multipolar behavior you'd expect from an industry still genuinely uncertain about which specific technical approach will ultimately prove most durable over the coming decade. This is precisely the nuance and honest answer to this video's title actually requires. Did NVQ-Link work? On the narrow, specific, and genuinely important question of whether the interconnect delivers the real-time performance it originally promised, the evidence is remarkably strong and remarkably well verified. Independent hardware validation from Dell, concrete technical integration from a genuinely diverse spread of quantum hardware companies spanning nearly every major architecture currently being pursued in the field, detailed, independently authored case studies explaining precisely how and why the interconnect solves real, previously unsolved technical problems for specific applications like photonic quantum machine learning. That's not marketing. That's the kind of evidence trail serious infrastructure projects leave behind when they actually get adopted and actually get used, rather than quietly abandoned once the initial press cycle fades, but on the broader, more sweeping question of whether NVQ-Link single-handedly conquered the quantum classical integration market the way some of the earliest, most excited commentary predicted. The honest answer is considerably more modest. It became a genuinely major, genuinely credible standard, adopted widely enough to matter enormously to the industry's overall trajectory. It did not become the only standard, and the emergence of HPE's competing Cray-based coalition alongside IBM's continued independent path proves that this industry, even 9 months after Nvidia's confident Rosetta Stone framing, remains genuinely unsettled about exactly which piece of shared infrastructure will ultimately win out. Consider, too, what the Quantum Insider, an independent trade publication with no financial stake in Nvidia's specific commercial success, had to say about NVQLink's broader significance as this first year progressed. Their assessment described the interconnect as an obvious sign of convergence between what they called the two fastest-moving frontiers in all of computation: accelerated classical computing and quantum hardware. Notice the specific framing embedded in that assessment. Not a verdict on whether Nvidia specifically wins this particular race. A recognition that the underlying trend NVQLink represents, deep, genuine integration between quantum and classical infrastructure, has become an undeniable industry-wide reality, regardless of which specific companies interconnect, ultimately proves most enduring over the coming years. This distinction matters enormously for understanding NVQLink's true first-year legacy. Even if some future, currently unknown standard eventually displaces NVQLink as the industry's preferred interconnect, the underlying architectural pattern it pioneered, real-time, microsecond-level coupling between quantum processors and classical GPUs, has already become the accepted, expected shape of how this entire industry believes quantum computing must eventually scale. Nvidia may not have permanently won this specific race, but it appears to have correctly identified and successfully proven out in working, independently replicated hardware, the exact shape the race itself needed to take. Think about the deeper significance of that specific kind of success, because it's actually a more interesting, more nuanced outcome than either the breathless launch day hype or a simple failure narrative would have predicted. Technology history is genuinely full of examples where the company that first proves a new architectural pattern works doesn't necessarily end up being the company that ultimately dominates the market, built on top of that pattern. Early web browsers proved the internet could be navigated visually, even as different companies eventually came to dominate that exact market years later. Early smartphone manufacturers proved touchscreen computing was viable, even as the specific competitive landscape shifted dramatically in the years that followed. NVQLink's actual first-year legacy may end up looking considerably more like this specific historical pattern than like Jensen Huang's original. More triumphant framing suggested, not necessarily the permanent, unchallenged winner of quantum classical integration, but very plausibly, the project that proved conclusively, with independently verified hardware and a genuinely diverse cross-architecture coalition of real adopters, that this entire category of infrastructure was not only technically achievable, but achievable specifically at the microsecond level speeds quantum error correction actually demands. So where does this leave the honest, carefully researched verdict on the specific question sitting inside this video's own title? Did Nvidia's quantum bridge actually work? The evidence gathered across its first 9 to 10 months in existence supports a genuinely affirmative answer, but a precisely qualified one. Exactly the kind of nuanced verdict that respects both the real, independently verified technical achievement and the genuine limits of what that achievement has actually proven so far. The core latency promise held up under independent scrutiny. The partner ecosystem grew from a launch day list of companies simply signing on into a genuinely diverse group of businesses building real, load-bearing products and publishing detailed technical evidence, explaining exactly why the interconnect mattered for their own specific corner of quantum hardware. And the underlying architectural vision, tight, real-time coupling between quantum processors and classical GPUs, has become something close to an accepted industry consensus about the shape quantum computing infrastructure genuinely needs to take, even among companies that ultimately chose not to build on NVQLink specifically. What hasn't yet happened, and what an honest assessment has to acknowledge clearly, is the kind of singular market-dominating victory some of the earliest coverage predicted back in October of 2025. IBM continues its own separate path. HPE has assembled its own credible competing coalition. The industry, even after a genuinely successful first year for NVQLink specifically, remains meaningfully more contested and more multipolar than a simple story of total Nvidia dominance would suggest. If you want to understand exactly what happens once NVQLink actually reaches its true one-year anniversary this coming October, and whether the momentum documented throughout this first 9 months continues to build, or whether HPE's rival coalition and IBM's independent path begin pulling meaningful market share away from Nvidia's early, hard-won lead, that's precisely the story we'll be tracking closely as it continues to unfold. So make sure you're subscribed before that full-year verdict finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the genuine, independently verified evidence of NVQ-Link's technical adoption across such a genuinely diverse range of quantum hardware companies convince you this interconnect has already won its category? Or does the continued presence of serious, credible rivals like IBM and HPE make you think this entire industry is still years away from settling on a single, lasting standard? Leave your honest answer down in the comments below, and as always, I read every single one.